Hello, everyone. I'm Satya Ramaseshan, and I lead product for Elastic Load Balancing and API Gateway. With me, I have Yusuf Warabi, who leads engineering for API Gateway, PrivateLink, and VPC Lattice. We're both extremely excited to be here today and to share with you the latest on the services that we work on. This is a 300-level class, so I'll kick things off by first defining the term application networking and then providing an overview of all the services in the portfolio. The intent of this section is to give you a good understanding of these services relative to each other so that you can make an informed decision on which service to choose based on your architecture. We'll then move to a deep dive section where I will cover elastic load balancing and then turn things over to Yusuf, who will cover the rest. Hopefully, you are an application developer, a network engineer, or an IT professional who's interested in learning about how the network can simplify application development. So in AWS, we always work backwards from the customer. And in this case, we're working backwards from two specific personas, the network admin and then the developer. Our belief is that the network admin wants to empower developers without losing control. Towards this, they need a centralized set of tools to connect and secure applications. For example, a network admin cares about how two IPs in their network connect and how secure the communication is. They don't necessarily care about what's behind those IPs. Developers, on the other hand, care about the application, not the network. They want to build their applications as efficiently as possible. That is, they want to build their business logics as efficiently as possible. To extend the previous example, an app developer will care about the features and performance of their application and not the IP that it resolves to or the subnet that it sits in. So application networking is the glue that helps these two personas work together to build highly scalable, reliable, performant, and secure applications using fully managed AWS services. Today, the main services in AWS's portfolio that cover this topic are Elastic Load Balancing, API Gateway, AWS PrivateLink, and Amazon VPC Lattice. The thread that connects these four services together is their required functionality. Availability and scale, for example, is a fundamental feature of all fully managed services in AWS. And for us, each one of these services automatically scale based on the traffic that they receive and can be deployed across all of the AZs in a region. In addition to availability and scale, each one of these services can connect, secure, and monitor your applications. They provide these features in varying levels, and this will be something that we'll continually explore during the course of this talk. To build a mental model, I'd like to start by introducing the TCP/IP model, which is a simpler version of the OSI model that you may be familiar with. The model talks about how the networking layers interact with each other in order to facilitate communication between two systems. So there are four total layers. So let's start with the network access layer from the bottom. This is the physical layer, and this is actually the layer that we won't be covering in this talk today. Above that, we have the network layer, where IPs are added to each packet, so there's IP awareness in this layer, and they're forwarded to the destination using route tables. Above that, we have the transport layer, where packets are transmitted between sender and receiver based on protocol, TCP or UDP. This particular layer has awareness of connections, flows. In addition to that, it has port awareness. And then up top, we have the application layer, which is the request response layer. Now that we've gone through the basics, let's work through an example. Let's say a client formulates a request. It says, get some resource from a server. It goes from the application layer to the transport layer, where it's broken down into packets based on the protocol, and ports get added to it. Then it's sent to the network layer, where each packet gets IPs, and then the physical layer is used to route the packet to the destination. At the destination, the receiver first strips off the IPs, sends it to the transport layer, where it ensures that the packets were received in order of the protocol that they chose, and then they take out the ports, and then it's sent to the application layer, where the packets are formed into the request, which a server can respond to. Almost all of the services in application networking fall either under the transport layer or the application layer. So let's talk about the services in the transport layer. The first service that I'd like to talk about today is the network load balancer, or NLB, which is a connection-level load balancer that can load balance both TCP connections and UDP flows to targets that are instances or containers. The network load balancer is an extremely popular way to expose your services inside the VPC to the internet, or to spin up an internal load balancer that can give you client-to-target connectivity within the VPC. NLB is typically used for applications that require massive scale. From a security standpoint, NLB can encrypt traffic with TLS. In addition, it can give you IP-based access controls using security groups. Security groups are simple and intuitive and are highly leveraged by admins for IP-based security. The next service that I'd like to talk about is PrivateLink, which is another transport layer service that offers inter-VPC connectivity by exposing a unidirectional connection between an interface endpoint that lives in a client VPC to a service behind a network load balancer. This connectivity is established using the AWS backbone, which is both performant and secure. PrivateLink also introduces this concept of provider and consumer. A provider is a service owner. It can be an AWS service, say CloudWatch, a customer-owned service, or a service offered by a third party like an ISV. The consumer is the entity that uses the service. And for us, the consumer and provider, apart from being in separate VPCs, can also be in their own accounts. From a security standpoint, PrivateLink mirrors NLB. So you get security groups as well as TLS encryption between the interface endpoint and the network load balancer. The next service I'd like to talk about is the gateway load balancer, which is a unique service. And it's unique because it has properties of both the network layer as well as the transport layer. What gateway load balancer is a protocol-agnostic bump-in-the-wire, which is both a layer 3 gateway and a layer 4 load balancer. So this protocol agnosticism makes it more of a network service than a transport service. It does mimic a load balancer because it is able to load balance connections to application targets. And it is a layer 3 load balance gateway because you configure a next hop in a route table to get to the destination. GWLB, or Gateway Load Balancer, uses Geneve for NCAP decap for its bump-in-the-wire implementation. GWLB primarily operates in the security space where it's leveraged by customers to deploy highly available firewalls that they have either built on their own or from third-party providers for intrusion detection and prevention. So as far as the traffic flow through this goes, when traffic outside the VPC, so traffic from outside the VPC that it was deployed in, it can be internet or a different VPC, comes through to the gateway load balancer endpoint, which is an interface endpoint, so think PrivateLink. From there, it gets forwarded to the appliance target, and then from there, it gets inspected and then goes to the destination. So next, we're going to move further up the stack and then talk about services in the application layer. And we're going to start with the application load balancer, or ALB. The ALB provides request-level routing and load balancing to targets that are containers, instances, and maybe even serverless applications. This is the most popular load balancer within AWS to expose services that are within the VPC to the internet. Like NLB, you can also have an internal ALB for in-VPC connectivity. ALB is super popular because it has broad appeal across a variety of workloads, like hosting websites, API servers. It plays in a variety of industries like media, streaming, gaming, fintech, enterprises, ad tech, et cetera. From a security standpoint, you can do much more at this layer. So for starters, the ALB has features of the NLB, which is TLS as well as security groups. In addition to that, in terms of TLS, we support mutual TLS, where you can authenticate certificate-based identities from the client at the load balancer. You can do user auth through Cognito. It can even do user auth at a third-party IDP, as long as it is OIDC compliant. Outside of the auth space, it has integrations with AWS WAF, which can further enhance the security posture in your data path. Next, I'd like to talk about API Gateway, which is a higher-level abstraction that is used by developers to create, publish, maintain, monitor, and secure APIs at any scale. Comparing ALB and API Gateway, ALB is best suited for simpler API servers, whereas API Gateway's feature set makes it suitable for advanced use cases. API Gateway can provide you a public endpoint to APIs built using several AWS services like Lambda, DynamoDB, S3, or services that of your own that are in the VPC. You can either have a regional endpoint or an edge-optimized endpoint, where an edge-optimized endpoint has a CloudFront distribution in front of your API gateway, and that CloudFront distribution is managed by AWS. A key attribute of API gateway, as you can see, is it lives outside the VPC, and so it simplifies user experience because you don't have to place those API gateway resources inside your VPC. Now, if you want to expose your APIs just internally within your AWS environment and restrict access to the public internet, you can use private APIs. API Gateway supports private APIs through its integration with AWS PrivateLink. From an application awareness standpoint, API Gateway is the only service within our portfolio that has awareness of the request and response body. And with that, you can do some interesting things. For example, let's say you want to have very specific fields in your request body. Say, first name and last name. The API Gateway can reject the request by sending a 400 if it doesn't find it. Now, in the happy path, in case you do find what you're looking for, you can use API Gateway to transform the request. And in this case, I'm showing an example where first name and last name is concatenated to just name field, and then it's sent to the destination. Similar capabilities are available on the response as well. Another useful feature of API Gateway is usage plans, which can be used to throttle or track APIs based on client or method or a combination of the two, which is extremely useful if you want to productize your APIs. From a security standpoint, API Gateway can do much more than ALB. So you have TLS, mutual TLS, user auth with Cognito. You can use IAM-based auth if you want to authenticate AWS principals. And if you want to run your custom auth logic, you can use Lambda Authorizer. So what happens when you put both the transport layer and the application layer together? For us, it looks like VPC Lattice. Lattice is a unique service. Again, it's a higher level abstraction that simplifies networking for both admins and developers by providing intuitive persona-specific features. For example, Lattice provides inter-VPC connectivity at scale. That is, many services that are spread across multiple VPCs can be connected by Lattice with a single instantiation of Lattice called a service network. This is extremely useful for network admins because they can not only connect all of these services across so many other VPCs at scale, but also they don't have to worry about any kind of IP overlap issues, et cetera. Like API Gateway, Lattice also lives outside the VPC, so it simplifies UX because you don't have to place the Lattice resources inside your VPC. Another key feature of Lattice is its service directory, which is an inventory of all the services within your service network. This is extremely useful for discovery and is especially applicable when you have a large number of services in your service network. From an application awareness standpoint, Lattice can do request routing and load balancing, which is very similar like an ALB. From a security standpoint, Lattice has a bit of the properties of ALB, so security groups and TLS, encryption between two services. It's extremely feature-rich when it comes to auth. Lattice supports IAM-based auth, and it supports it at two levels. At the service network level, where a network admin can have coarse-grained auth policies, and then at the service level, where a developer can have finer-grained auth policies. Lattice also does authentication of SIG-v4 requests before it reaches the destination. So the combination of features of Lattice, inter-VPC connectivity, layer server awareness, the feature richness in the auth space makes it an ideal fit for zero-trust type architectures. So we've covered a lot, so let's do a quick recap. Please feel free to take a photo of this. A key takeaway is by using application networking services and its integrations with other AWS services, you can achieve high availability and a strong security posture for your applications. When you compare Elastic Load Balancing with API Gateway, ELB, or Elastic Load Balancing, is best suited for load balancing use cases and perhaps simple API servers. API Gateway for advanced API server use case, API server advanced hosting of APIs at scale. And then when you compare PrivateLink and Lattice, PrivateLink, by the way, has integrations with both elastic load balancing as well as API gateway. PrivateLink is for point-to-point connectivity, and Lattice is for many-to-many or mesh-style connectivity. And Lattice also plays in the zero trust space. So that brings us to the end of the overview. So let's get into the deep dives, starting with elastic load balancing. So there are 4 total load balancers. We've talked about ALB, NLB, and GWLB. The classic load balancer, CLB, is the first load balancer that we launched. It is capable of both layer 4 and layer 7 load balancing, and it is an option that we continue to maintain. In this section, I'm going to be covering key feature launches of ELB over the last 12 months. Security is always a top priority, and so we've invested in features there. 2 features I'd like to talk about is shared security groups on ALB and NLB, and enhancements to the mutual TLS offering. So shared security groups is actually a feature of the VPC that was launched earlier this year. Both ALB and NLB respect it. There are 2 use cases. First, you have a single VPC that is across multiple accounts, and now you can have a security group that can be placed in that VPC that works across all the participant accounts. Next is you have a single account but multiple VPCs in it, and you can share a security group across the VPCs that are there in that account. So again, this is a feature that the VPC launched, and both ALB and NLB support it. Mutual TLS was a feature that we launched last year. And when we launched the feature, the trust store, which has the CA bundle as well as the revocation list, had to be in the same account as the ALB. I'm happy to say that earlier this year, we launched trust store sharing, where you can share a particular trust store from a central account to various other application accounts using the AWS Resource Access Manager. So if you were a network admin, you can now generate a single trust store and make sure that all your application accounts are just using that trust store. So the security admins can easily scale while maintaining accuracy. Another feature that we launched is advertising the subject name in the CA bundle. So oftentimes, clients have more than one client certificate in them, and they need to choose the right client certificate to participate in that mutual TLS connection. This feature helps with that. Both of these features will launch based on feedback that we received from you after our mutual TLS launch. I hope you find these useful. Availability, again, is a top priority for elastic load balancing. A couple years ago, we launched, so a great way to architect for availability is to have your load balancer spread across 3 zones. And this is useful because even if you had one of the AZs impaired, you have an additional availability zone of additional AZ of availability. Now, a couple years ago, we launched a feature. Actually, it was the AWS Application Recovery Controller team, ARC, that launched a zonal shift feature for which we enabled cross-zone disabled load balancers. I'm happy to say that we've now enabled cross-zone enabled load balancers with zonal shift. With that, when you detect an impaired AZ and you choose to vacate it, we not only take out the load balancing nodes, but also the targets behind it. So the targets in the impaired AZ won't receive any traffic from nodes of the load balancer that are in healthy AZs, which reduces your scope of impact and improves your availability posture. Another feature that we recently launched is load balancer capacity unit reservation, which is available on both ALB and NLB. With this feature, you can set a minimum floor for load balancer capacity to handle a surge in traffic. For example, streaming a sports event, or you have an e-commerce platform that needs to support a flash sale, etc. You can simply specify a floor in load balancer capacity units, or LCU, and you're guaranteed to have that minimum capacity at all times. It's important to note that the load balancer will continue to auto-scale based on the traffic it receives beyond the minimum floor. So you can, overall, you get a floor based on the minimum capacity you set, and then organic scaling kicks in if you need more than that. Routing features are extremely useful on the load balancer because you can offload that logic from your application and thereby simplify your application. And we've launched a couple key features in this space. On NLB and GWLB, we launched TCP config idle timeout, which was a top requested ask. Prior to this launch, the TCP config idle timeout was set at 350 seconds. Now you can choose any value between 60 seconds and 6,000 seconds. With that, you can configure your load balancer timeout to match your clients and targets, which can potentially reduce retries, errors, overall reducing latency that increases the performance of your application. ALB header modification is another top requested ask, and there are two parts to this feature. On the request side, we've launched a specific capability to rename AWS-generated TLS headers. So we've learned from customers that TLS headers have special meaning for app developers because it is often used by organizations to enforce a minimum cipher version, or for compliance, or in case of mutual TLS, to build custom auth logic. And we heard from customers that it was hard for them to have to parse specific AWS-generated headers across various teams in order to build that logic. So to simplify that, we have now given you the ability to rename these headers. In this example, I'm showing Amazon TLS version being renamed to just TLS version, which maybe better suits your application before it goes to the destination. I will note that with this launch, you can only rename the headers. You cannot change the value. On the response side, we're giving you the capability to insert HSTS and cross-origin resource sharing of course headers. Now, the reason we launched this particular feature is to give admins the ability to centrally enforce these headers for the organization, because otherwise you'd ask individual application developer teams to do it, which can be prone to errors. So in this example, I'm showing adding a HSTS header, and the max age value is set to 900, but you have the ability to change it to whichever configuration suits your application the best. You can do the same with all of the course headers that are available as well. Both ALB and NLB are extremely popular with with Kubernetes deployments in AWS. So I'm going to dive into the AWS load balancer controller enhancements that we've made over the last 12 months. So let's start with the basics. The load balancer controller helps manage elastic load balancers for Kubernetes cluster. What I mean by that is the following. Within Kubernetes, customers like to interact with their Kubernetes resources using Kubernetes native APIs. The load balancer controller is a deployment within the cluster that serves as this translation layer between the Kubernetes APIs and the ELB control plane. In addition to that, it is also responsible for registering and deregistering pods within a Kubernetes cluster that make up a service as targets of a load balancer. This is especially important for Kubernetes because pods are highly ephemeral. The pods that make up the controller runs in 2 or more pods, and one of them is always elected as a leader. Within Kubernetes, when they say load balancer, it actually means layer 4 or NLB for us. And when they say ingress, it actually means layer 7 or ALB for us. Over the last 12 months, we focused on performance and usability improvements for the controller. The first area that we focused on to improve performance was reconciliation. So let's start with what reconciliation is. There are 3 components to be aware of. First, the controller. Next, the Kubernetes API server. And then there is the ELB control plane. Now, the role of the load balancer, controller rather, is to keep these 2 things in sync. So the green box that shows up means these 2 things are in sync. And this process, by 2 things I mean the Kubernetes API server and the ELB control plane, and this process of keeping them in sync is called reconciliation. But there are times when reconciliation can be pretty slow. For example, when you have a super large cluster, lots of services, lots of resources, and lots of load balancers attached to it, there is a lot of lookups that need to be done. And because of that, reconciliation can be slow. In addition to that, there are situations when the leader pod gets restarted. And in that case, a new replica needs to spin up, and then a new leader has to be elected, and then reconciliation has to happen, all of which can take time. As you can see, the green boxes are taking a little bit of time here. I'm happy to say that using caching and deferred queues, we've been able to reduce the number of lookups, and because of which reconciliation times have actually been reduced by 90%. So as you can see, those green boxes showed up very quickly in this slide. In addition, we've also upgraded the SDK that runs in the load balancer controller pods. It is useful to remember that the load balancer controller is actually a client of the ELB control plane, and it makes a lot of API calls for the reason that pods are ephemeral and they keep spinning up and down. We've upgraded the SDK that runs within these controller pods to AWS SDK Go v2, and with that, we get a 50% reduction in memory utilization. We get a 32% reduction in memory footprint. So this lighter weight SDK processes data much faster and also has an enhanced retry mechanism, all of which makes API calls extremely efficient, and so the controllers become more performant. We've heard from customers that they would like to build more resilient applications by provisioning multiple clusters to save traffic for their applications. Now, it is useful to note, again, that clusters, when they are two separate clusters, they have their own instantiation of the load balancer controller. So here, there are two clusters, two instantiation of the load balancer controller, and they're both separate from each other and independent from each other. And so when you spin up a target group across these two clusters, originally, the way we built it was to overwrite the target group. Each controller would overwrite the target group to avoid collisions. While this was great at avoiding collisions, it did not support a target group that could work across multiple clusters. I'm happy to say that we've now upgraded our controller to simultaneously onboard targets from multiple clusters without introducing conflicts. This enhancement allows us to support target groups across multiple clusters safely, which is a key usability improvement. So here I'm showing an example where you have a target group that stretches across two clusters within the same VPC. We also support target groups that stretches across two clusters in different VPC. You just need to use a service that does inner VPC connectivity in tandem, and here I'm showing Transit Gateway. That brings me to the end of my portion of this presentation. I'm going to turn things over to Yusuf now.
Thank you, Satya. That was a great introduction and really set the stage for what we'll go over next. In my section, we'll talk about API Gateway first, then PrivateLink and Lattice. Let's start with API Gateway. API Gateway is a service that enables anyone at any scale to publish production-ready APIs. Originally, standing up an API requires a certain amount of operational heavy lifting. Developers have to set up DNS records, TLS certificates, load balancers, web servers, et cetera. Customers asked us for a better way, and in 2015, we created API Gateway to make this easy. At first, we were heavily integrated with Lambda, and over time, we built on API Gateway to support other use cases. Let's take a second and review the core capabilities of API Gateway. At the core, there are HTTP RESTful APIs. These follow a request-response pattern. We support public APIs, that is, internet-facing APIs, as I mentioned. And over time, we added the ability to have private APIs, that is, internal to a service, internal to a private enterprise organization. Later, we launched WebSockets that for applications that needed streaming or asynchronous workloads. And we integrated with over 100 AWS services as targets of API Gateway. Additionally, API Gateway will perform authentication, authorization, throttling, usage keys, and so forth to help customers manage their APIs for their platform. API Gateway has been on a journey over the last couple of years. Feel free to take a picture of this, but in 2023, we announced that we had published or received well over 100 trillion API requests over 23, and that figure is continuing to grow at a rapid pace. As we continue to scale, we realized we needed to make a series of investments to meet the high standards our customers have on both availability and security. We're going to dig into these next. Starting with resilience, we made a number of improvements to better manage AZ failure events. We built a series of performance improvements in API Gateway itself, which allow us to scale thousands of nodes quickly. We built internal tooling that let us actually pluck out a single API stream and detect anomalies. For example, if a customer does a deployment and they see a spike in 500 errors, in our metrics, we can quickly detect that. We also built a number of usability improvements for developers on API Gateway. We built self-service quota management. We refreshed our console in early 2024. And we have partnered with a number of integrations, third-party integrations, to provide developer portal capabilities. We're going to dig into the resilience improvements first, and then go on to some lower-level data plane architecture slides. On resilience, as I mentioned, we built gray failure detection and mitigation. What that means is API Gateway has the ability to detect network-level impairments and will automatically mitigate and manage that for our customers with no action required. We built a series of service protection mitigations. We integrate with WAF at our scale and on the internet-facing APIs. It's not uncommon to come under a DDoS attack. Our teams respond 24/7 and will manage and mitigate these events for our customers. We also built the ability, as I mentioned, to increase decrease the time, it takes to provision large number of compute instances for our API platform. And lastly, we rebuilt the data plane and partitioned it into a cellular architecture. This is what we're going to dig into next. But first, we need to take a high-level overview of what is the path of an API request. So typically, requests follow a request response pattern. They come to some API system. Typically, at that point, authentication is performed, request validation, response validation, transformations, which API supports. And then that request is forwarded to some other service, a web server, a Lambda function, an EC2 instance, and so forth. When you invoke an API, at the first step, that a request will land on API Gateway's front door. That request is then routed internally to a first service, and that first service performs the first layer of security. This is where authentication, authorization, rate limiting, and so forth happen. And then, depending on the specific API that is then mapped out to one of the cells or partitions, we use a number of schemes, including shuffle sharding. This diagram on the far right is actually what we're going to go one level deeper on and expand upon to kind of help visualize this. When a request comes in to the first API, it is, after authentication, it is then passed out to a specific partition that owns that API. That partition has fully standalone infrastructure. It is a fully set of isolated load balancers. And again, we have thousands of load balancers. And then those load balancers have a set of compute instances that actually process the API invoke on the back end. These are isolated from each other and help us better scale and individually manage these partitions individually and control the blast radius of an individual partition on API Gateway. We've spoken a bit about the availability improvements that API Gateway has delivered over 2024, but it's also important to call out some of the key security features that API Gateway has launched. Earlier this year, we launched TLS 1.3 support for all of our APIs out of the box, no action required. This is part of our promise to customers of API Gateway. We also improved our integration with WAF and now can support large payload inspection for customers that are integrating WAF and API Gateway, supporting payloads up to 64 kilobytes. And for people on API Gateway that are using custom authorizers, we made a series of improvements to our authorizers to better support VPC endpoint policies. But we also got some feedback on usability. As I mentioned earlier, when API Gateway first launched, it was very heavily focused on public or internet-facing APIs. Over time, more and more private API patterns emerged, and this is where our customers have asked us for usability improvements. Embedded in an API Gateway endpoint is a lot of information. You have an API ID, you have a VPC ID, you have a region name, you have an API stage name, etc. What customers want is something simple and easy to remember, something like myexample.com. And they want to be able to share this with their customers and have it be quick and easy to discover. Over time, as private API patterns have become more and more common on API Gateway. This has become our #1 feature request. And I am happy to say we have listened and we have delivered. Today I'm announcing private custom domains is available for API Gateway. With private custom domains, we're actually opening a new chapter in API Gateway. First and foremost, this gives people better control over the custom ability and discoverability of their private API endpoints. Additionally, we're beginning to layer in features that make it easy to manage APIs at scale. With this release, we introduced the concept of a private domain, and then one or more APIs is mapped to that private domain. Developers can apply policies to the domain level and have all those IAM policies apply transitively to the APIs that are associated with that domain, making the policy and security management of private domains easier. Additionally, we've integrated deeply with both PrivateLink and Resource Access Manager, RAM, to seamlessly enable cross-account and cross-VPC sharing within an enterprise. So as you may know, AWS well-architected strongly suggests that customers operate in a multi-account, multi-VPC setup. And this is to better control security, better control blast radius. With private custom domains on API Gateway, you can easily support applications that have cross-VPC, cross-account clients without having to do that heavy lifting. Additionally, we integrated with IPv6 at launch. So private custom domains supports IPv6 at launch, and going forward, all API Gateway feature launches will support IPv6. Getting started with private custom domains is fairly straightforward. There are a couple of prerequisites, and feel free to take a picture of this if you want to. As an application owner, you will need an SSL or TLS certificate, and a Route 53 hosted zone. Typically, those certificates are managed by ACM. On API Gateway, you create the custom domain and create a base mapping for that domain. You then share that domain with Resource Access Manager, and this is so that you can share this API across account boundaries. You create you associate that domain with a VPC endpoint, and then you work with your customer and create the Route 53 mapping or alias to that custom domain. We're not going to go into too much depth here, but if you're interested in learning more, there is a session on Thursday, scaling private API workloads with API Gateway, where we'll go in depth on public patterns, private API patterns, and we'll hear from a large customer of ours, Itaú Unibanco, which is a large Brazilian bank that uses API Gateway extensively. If you're interested in learning more, I encourage you to check out that session on Thursday. Now we're going to pivot our attention to PrivateLink and Lattice, which both support private VPC connectivity, but in a different way and for slightly different purposes. PrivateLink supports unidirectional access from a consumer to a provider. This is client initiated. That is, a client has to take action to connect to a provider in a remote VPC. And optionally, the provider can implement a handshake protocol to accept or reject the connection. Traffic is guaranteed to remain private to AWS's network. And PrivateLink also supports on-premise network connectivity. That is, if you have an on-premise network and you connect into AWS's VPC over DX, you can then access a service over PrivateLink transitively through that VPC. Customers love using PrivateLink for a variety of reasons. First and foremost is the client initiation. This is really powerful for crossing trust boundaries, across an organization. A common use case might be accessing a third-party database. For example, MongoDB, which offers a PrivateLink solution. You, as a consumer, want to access a managed MongoDB instance in their VPC. You do not want them to have any access to your network. And that's where the client-initiated unidirectional aspect comes into play. Additionally, with policies, endpoint policies, and security group, you can build a very powerful data perimeter for your enterprise network that controls who connects to what endpoint and will give you strong security and compliance guarantees. As mentioned, PrivateLink also supports on-prem connectivity. On the provider side, PrivateLink also vends a lot of metrics and telemetry. PrivateLink recently launched a feature called Contributor Insights that gives providers insights into top consumers of the API, top talkers, and so forth to help them manage the connection. There are two types of services that a PrivateLink endpoint will connect to. TCP services and appliances. We're going to focus more on services today, but it is worth talking briefly about appliances. Appliances are PrivateLink's integration with Gateway Load Balancer. Gateway Load Balancer provides the ability to have advanced functionality, typically at lower levels of the network, and integrate them into your network with a Gateway Load Balancer endpoint, which is powered by PrivateLink. In this talk, we're going to focus more on services. There are historically, services on PrivateLink have been TCP only, and they fall into three categories. First are AWS services, and many customers connect to AWS services over PrivateLink. Today, PrivateLink supports over 190 AWS services, and that number is constantly growing. Second category are customer developed or customer-owned services. This goes back to private enterprise patterns where you may have a service that you want to expose data and you want to have your own enterprise customers access that across VPC and across account boundaries. PrivateLink will help you do that. And lastly are third-party providers, Third-party providers are services like MongoDB, Teradata, Snowflake. PrivateLink both integrates with AWS Marketplace, but also has its own ISV ecosystem for third-party providers where they can offer services over PrivateLink. A limitation historically has been that these services must be TCP powered or based on TCP protocol. Customers have asked for expanded connectivity and critically support for UDP connectivity. And today I'm happy to announce that we have released UDP support for PrivateLink. This is generally available in all regions. And critically, this actually supports both UDP v4 and v6 at launch. And we'll talk about this more because the extensibility, composability, and interoperability is actually a big theme in the next coming slides. So with this release, you can actually add UDP v4 or v6 listeners to an NLB in an architecture, and feel free to take a picture of this diagram as well, allowing you to seamlessly migrate or incrementally migrate to v6 providers, services. And it doesn't require a bigger architecture redesign. You can use as long as the NLB powering the PrivateLink service is dual stack, you can use it in place and incrementally add listeners. This is a profound improvement to PrivateLink's connectivity and usability, but our customers have asked us for more. What we've heard from customers is they want the ability to connect to PrivateLink across regional boundaries. So expanding on the same diagram, what they would like to see is have a consumer or customer in US East 1 access data or a provider service in US West 2, for example. Sometimes this is because they want their data to live in a specific region. Sometimes this is for internal disaster recovery failover scenarios. I'm happy to say that we've delivered a new capability. Today we're announcing cross-region PrivateLink. This is generally available in 7 regions right now, and by January 2025, it will be available in all regions. Further, if you go back to the previous slide, this works out of the box, both UDP and TCP services across region boundaries, and v4 and v6 connectivity across regional boundaries, which will enable a lot of use cases that we're actually excited about. We've already received some really strong feedback from key partners. In the words of Salesforce, this enhancement will allow us to streamline inter-region communication for both internal and external services without compromising security, performance, or scalability. From Datadog, we hear that with cross-region PrivateLink, customers can send observability data to Datadog in just a few clicks without creating networking resources in multiple regions. So I mentioned that PrivateLink has a group of third-party ISV partners. There are too many to call out, but we did want to highlight some of our key partners on PrivateLink, and we're always working to grow this. So if you're interested in becoming a PrivateLink partner, please reach out to me. Additionally, as I mentioned, Gateway Load Balancer has a similar provider system, ISV system. Again, we have key partners up there. If you're interested in becoming a partner, please feel free to reach out to me. Now that we've talked about PrivateLink, it's actually important that we pivot to Lattice. I mentioned previously that PrivateLink was very well suited toward crossing a trust boundary, that is from within your organization to another organization. Lattice typically is used within an organization, although it has very strong data perimeter and security controls, and we'll talk about that in coming slides. But it can be a natural fit for within a trust boundary. Lattice introduces 4 concepts. They're relatively straightforward, but it's worth unpacking them and going a little bit deeper into Lattice concepts because they're actually going to enable some really cool announcements that I have to make. First is a Lattice service. A Lattice service is, think of it as an application endpoint. A service network is a collection of services, one or more services. And this grouping primitive, this grouping abstraction, actually helps you share and manage your applications in a really elegant way. There are auth policies, IAM policies that can be applied to both service networks or services individually. And lastly, there's a service directory, which is a discoverability tool to discover the services in a service network. This is important when there are a lot of services in a service network. Customers love using Lattice for many reasons, among them better abstractions. So, thinking back to PrivateLink is a point-to-point client-initiated connection. This is really simple and it's great to get started. But at scale, managing thousands of PrivateLink services and thousands of PrivateLink connections can become a challenge. The abstractions that Lattice provide help developers manage those scenarios and help scale elegantly. The policies, the fact that policies can be applied to services or service networks help you easily apply fine-grained control. Lastly, and this is something that I'm the most excited about and we'll talk about in detail, are application awareness, which helps developers kind of do operations like throttling and heavy lifting. And critically, Lattice is compute agnostic. And what that means is you can define a Lattice service to be backed by a Lambda function, for example, or an EC2 instance, or a Kubernetes cluster. You can, if you have an existing EC2 instance, you can use that to power your Lattice service. If your developers decide, hey, actually Kubernetes would be a great fit for this workload, you can do that without changing anything else in your architecture. Simply create a new Lattice service backed by Kubernetes, and you're off to the races. We're going to go, before we talk about some exciting announcements, we're going to take a little bit of a deeper dive on services and service networks. A Lattice service has 4 components. A URL is the first component. Second is a listener, and this is where you define ports, protocols, how clients connect. Rules, routing rules effectively, where to emit invokes to the Lattice service. And lastly, target groups. And this is what I mentioned. We support a variety of compute options today. It could be an EC2 instance, a Lambda function, an EKS cluster, or another load balancer, right? If you already have a load balance service, you can create a Lattice abstraction on top of that and layer that into your mesh. Service networks are the grouping mechanism. They're also the association mechanism, and they help you organize services. You can connect a service network to one or many VPCs, and we'll actually dig into this in coming slides. And we actually have some really important announcements. We're actually introducing new primitives by way of Lattice. Getting started with Lattice is fairly simple. You first create the Lattice target group or the targets. This is the application, the thing that will process the requests. you can create the Lattice service itself and point it, associate it with those targets. You then create the Lattice service network, and then you associate that service network with one or more VPCs. Lastly, you can associate the services to the service network. This scales elegantly, as you can see if you go back to this slide, where once you have your service network defined, you can seamlessly add thousands of VPCs associated with it. And what that lets you do as a developer is create multiple small accounts, multiple small VPCs to better partition your security boundaries, but still associate and share them with the same service infrastructure. So you're not repeating this multiple times. And this abstraction lets people create fairly advanced topologies that are secure, that have high-grained control relatively easily. So, and this is what I'm really excited about. If you go back, as I mentioned, Lattice is compute agnostic. Here you see I kind of swapped out the generic Lattice service logos with EC2, with Kubernetes, with Lambda. And Lambda is an important part of our ecosystem. But customers have asked us to complete this integration portfolio with support for ECS. This was typically previously possible with some customer-owned workarounds. What I'm showing here is what that would look like. I've labeled the boxes to make it conceptually clear, but you would define a Lattice service. That Lattice service would have a target, which would be a load balancer, typically an ALB. And that ALB would then proxy events to the ECS cluster. This was workable, but it was a workaround, and it introduced complexity and costs. Our customers asked for a better way, and I'm happy to say we've introduced native ECS support for Lattice. With this, we're actually completing the integration of compute options on Lattice's a Lattice service integration, adding one more compute engine that you may want to use. That your developers may want to use as you build new services. This is what that looks like. And simplifying, going back to the previous graph, you can see, or diagram, excuse me, you can see that we simply just removed the intermediate load balancers, and we can now natively emit calls to ECS tasks. Taking a step back, and this is what really gets me excited. The fact that Lattice has application awareness and is compute agnostic really creates a powerful tool. Feel free to take a picture of this as well. But what you can see is you can find different listeners. You can have different rules. Based off rules, for example, paths, you can route to different compute engines. For example, as I mentioned, if you start with Kubernetes and you decide that you actually need to migrate that workload to an ALB back service, Lattice will let you do that seamlessly without changing anything else in your topology, without changing your security policies, your data perimeter, your connectivity mesh. And our goal is to be the preferred mesh on AWS. Customers have asked me, how do we think about PrivateLink or Lattice? And I think it's a really interesting question. With this release, and this goes back to some of the primitives that we are introducing by way of Lattice and service networks, what I would suggest is we should think of PrivateLink and Lattice. So we mentioned how customers wanted expanded connectivity. They wanted to connect to UDP-based services. They wanted to connect to ECS-based clusters. But they've also asked for connectivity to non-load-bound services. This can be things like EC2 instances, databases, caches. These are typically not backed by a load balancer. Typically you wouldn't put a load balancer in front of your cache or your database cluster. This use case, we'll explore two different use cases, applies both on the consumer and the producer side. So customers typically want to access a specific endpoint, a specific resource in a remote VPC. In the case of an individual EC2 instance, this could be done, but you would have to create an intermediate NLB, create a PrivateLink service, and do that additional overhead just to support that PrivateLink connectivity. On the provider side, there are actually use cases where providers may have a specific need to connect back and access a specific controlled resource. A common use case would be if your company is building a data ingester or data collection service, and your customers have data on a single EC2 instance, right? You don't necessarily want them to stand up a PrivateLink service just for you to call back into, But you do want them to have controls, a data perimeter, and security guarantees around they're only sharing certain resources with you across VPC boundaries. Again, this is done, today, the workaround is similar. You would vend a automation, CDK or Terraform, and then have your customer set up a PrivateLink service and then call back into that. Today, we're actually announcing a new construct within Lattice and for VPCs called resources, which model the resources that I mentioned, EC2 instances, RDS databases, cache clusters. Resources are built for scale. They allow one-to-many or many-to-many communication, and they have the same strong integration with RAM and IAM policies. And today, I am happy to announce that we are launching cross-VPC resource endpoints. What this does is it will let customers connect to a single EC2 instance without the need for the additional load balance services. Getting started with resource endpoints is easy. As a resource owner using the Lattice APIs, you would define your resource or create your resource, and this concept exists within Lattice. You then create the policies, the resource configuration policies that you want for that resource. You can share that through RAM for cross-account sharing. You then, as on the consumer side, and this goes back to the interoperability that I mentioned, you can connect to that resource over PrivateLink or Lattice, right? So you can use an existing PrivateLink connection and connect directly into that resource, or you can add that resource to a service network and associate that with your VPC. So going back to this diagram that I shared previously, with this release, we're also announcing the ability for PrivateLink to connect to Lattice service networks directly. And a use case might be, assume you have an existing PrivateLink deployment, you have started creating Lattice services and your developers love it. You don't have to modify your architecture. We're building the bridge. Simply connect from your VPC deployment into the Lattice service network. Cross VPC resources provide many benefits. They're private, they're scalable, they allow one-to-many or many-to-many, and we integrate with RAM and IAM for seamless sharing. We're already getting really strong feedback from key partners that are using resource endpoints today. Palo Alto Networks says that the integration of resource endpoints with their next generation firewall marks a significant step forward in simplifying cloud operations. ClickHouse says that resource endpoints is a compelling feature for anyone moving data from operational systems hosted in AWS. ClickPipes is used to manage trillions of rows. Resource endpoints allows us to offer secure communication at a very granular level. And thank you to our partners. At launch, Resource Endpoints has a number of partners. Some of these were mentioned in the previous slide. Again, we don't have time to go into detail on all of them, but I wanted to thank them for their integration with Resource Endpoints, and I'm looking forward to the innovation that this will unlock for our customers. There are a couple of sessions that I recommend if you're interested in learning more about application networking. Right after this talk, there is NET317, which is advanced VPC design and what's new. Tomorrow, Tuesday, NET218, we'll have a deep dive on simplifying resource access with AWS PrivateLink and VPC Lattice. And on Thursday, there is the scaling and securing private workloads using Amazon API Gateway, which will be a deep dive on API Gateway patterns, and we'll hear from large customers. With that, thank you very much. I hope these announcements are interesting to you, and I'm excited to see what you will build with them. Thank you for your time. Please feel free to connect and reach out with any questions, and please remember to fill out the survey. Thank you.